Okay. So, useful energy and efficiency is what we're going over. Efficiency refers to what? And keeping in mind you can't use the word efficient in your definition. Okay, amount of useful energy, that's part of it. Okay, how effectively you use the energy, yeah. Okay, basically guys, efficiency is a percentage. Okay, it is a percentage that says if you had this much energy to work with, this is how much useful work you did. All right? So if you are working at 90% efficiency, 90% of the energy that's put in is getting used to do useful work and only 10% is being wasted. All right? Everyone follow me there? Now, yesterday we did that lab with energy conversions, and we found that most energy conversions are not very efficient. Okay, in fact, most of our groups found that it was somewhere around 10% or maybe even less, okay, for the conversion of the potential energy in the rubber band to the little dynamics cart. Okay, and that's a relatively simple energy conversion. Okay, the more complex the energy conversion, generally the less efficient it is. The more conversions you have to do between A and B, the less efficient you are going to be. All right, and that's kind of the problem that we're battling, okay, as a society that is very energy dependent. Okay, is how can we increase the efficiency, reduce the number of conversions, okay, and things like that in order to make the most use of our resources. Okay, so the purpose of any machine is to convert the energy, the initial energy that's given to it, into the type of energy that's needed to do the work you want done. Okay, all other types of energy are considered wasted, okay, or lost. Most of the time, what's the main wasted form of energy? Okay, heat's a transfer of energy. So what kind of energy does heat transfer? Thermal energy, okay? So yeah, we say it's heat because it is being transferred away. It's transferring thermal energy away. But yeah, in general, okay, thermal energy is what is produced in an inefficient system. Other forms, you could have sound, okay? Sound is usually accompanied by something or is usually caused by something inefficient, right? It's why, we can tell there's something wrong with our car. What do you do when you take it? It's making a funny sound. Right? Most of the time that's what's making a funny sound, or the check engine light came on. Okay? But usually it makes a funny sound when that comes on. Okay? Those are all signs that something's not right, something's not running efficiently. Okay? Sometimes light is also produced. If that's as a result of moving parts, it's also generally not a good thing. Okay? If they are making sparks, generally a bad sign. Okay? So light, sound, and thermal energy, okay, are all generally the forms of wasted energy that we can detect. Okay, so the initial source of energy is called our energy input. The desired energy is called the useful energy output. Okay, and the work the machine is supposed to do is the useful work output. So in a theoretical relationship, the useful work output and the initial energy should be the same. All right, but we know there's no energy conversion that's 100% efficient. Okay, and we have to understand that that's just not going to happen. Give you some idea. Your car, every day that you drive to school in, how efficient do you think it is? Without looking at the chart. Okay? Honestly, guys, would you accept, if you went, let's say, to the hospital, would you accept a doctor who was right 14% of the time? No. He would probably try to take out your appendix with a grapefruit spoon. Okay? Like, this is just not something you would accept. Yeah, that's where I got the idea from. Yeah, he had an appendicitis, took his appendix out with a grapefruit spoon. That would be pretty incredible, really. Anyway, back to the idea at hand here. 14% efficiency is about what your car runs. If you have, let's say, about a mid-size 6-cylinder sedan, okay? It runs at about 14% efficiency. More modern cars might get near 20. A hybrid vehicle might run near 25 if used properly. All right? Where is a hybrid vehicle giving you the most benefit? City driving or highway driving? City driving. Okay? If you bought a hybrid vehicle for all highway miles, you wasted your money. All right? On the highway, your hybrid vehicle runs mostly on the gas engine. Okay? The purpose of a hybrid vehicle is to use the electric engine to assist the gas engine under times of load. All right, so when you are accelerating, okay, and things like that, the electric engine kicks in and assists the gas engine. When there is no assist needed, it runs on gas. All right, so hybrid vehicles must be used efficiently under city driving conditions, stop and go traffic, not on the highway. Okay, otherwise you're just not getting the benefit out of them. All right, so around, we'll say on average 14%. If you drive like a large truck, it's probably less than that. Okay. Give you some idea. 33% of the energy available in your fuel. So let's say you put $100 worth of gas to make things easy. $100 worth of gas in your car. $33 is used by the exhaust system. Okay? What does the exhaust system do? Well, it does get hot. You can't grab onto the pipes of the exhaust once your car's been running for a couple of minutes. Okay? So there's a lot of heat there. Okay? But what is the purpose of your exhaust system? What does it vent? Right, all the harmful byproduct gases, carbon dioxide, carbon monoxide, sulfur dioxide, whatever comes out of your car, make sure that it gets vented to the rear of the vehicle and not into the passenger cabin where it would poison you. Okay? I'm not saying that that's not an important function, but it didn't worth $33 out of 100. Okay? There's just so much heat in those spent gases, okay? And they're not doing any useful work. Your exhaust does not propel the car forward. Okay, so that's lost. 33% right there. Okay, you have not moved forward yet. 33%. All right, cooling and heating system. $33 out of your $100 worth of fuel. Your car is so inefficient. It needs to use 1/3 of the energy you put into it to keep it from melting down. All right, I mean, you consider how a car works. Pistons move up and down. The pistons are made of metal. The cylinder they move in is metal. This is metal on metal all the time. Okay? Is there a lot of friction when you have metal on metal? Yeah, that's why there's oil in your car, by the way. Okay, it helps a little bit, keeps your car from seizing, which is very bad. So it's still a very inefficient system. So what you have to have on your car is a big pump called a water pump that pumps coolant through the engine block, okay, and absorbs heat energy from the block from the engine, takes it to the radiator, and you have a fan there that blows and runs and sends cool air across the coolant, and that vents the heat outside of the car. Okay, all of that heat came from the energy in your fuel. It isn't doing any useful work. All right, so you got heat loss there. You've got energy being used to run the pump, to run the fan. Okay, all of that kind of stuff. Is any of that propelling the car forward? None. All right, none of it's propelling the car forward. Okay, that would also include if you have air conditioning. Okay, your air conditioner has a separate pump. Okay, that also runs off of a belt that runs off of your motor, and it doesn't propel the car forward and reduces the efficiency of your vehicle as well. Drivetrain loss. Okay, this is anything that is a moving part. Okay, within, let's say, the drive axle, transmission, okay, limited slip differential, all that kind of stuff. Anything that is essentially attached to the wheels of your vehicle. All right, there is friction in there, and as a result, heat is produced and energy is lost. 10%. Your accessories. All right, if you have not done any significant modifications to the vehicle, that means putting in, 7 12-inch subs, 4 extra amplifiers to power them, okay, all of that kind of stuff. Then your accessories, stereo, windshield wipers, defogger, okay, power windows and door locks and all of that stuff, about 4%. So $4 out of your 100 is spent to play the radio, okay, while you are driving around. Internal friction, okay, so basically any other moving parts, okay, 6%, which leaves 14%. $14 out of the 100 is actually what propels your car forward. The rest of it, you might as well set fire to, because that's what your engine did. Okay? It's very inefficient, but we accept it. Every single day you get in your car and accept that it will run at 20% or less efficiency. All right? It's crazy. Okay? You wouldn't accept that from anything else, but you'll accept it every day when you get in a car. Right? I'm not saying it's a bad thing. I drive a big truck, and I just accept it too. Okay? But it's something that obviously there are regulations even being set on, okay, to make vehicles more and more efficient. All right? The vehicles we drive now are far more efficient than they were even 5, 10 years ago. All right. If you drove even a small car a few years ago, if you got 8 or 9 liters per 100 kilometers, you were laughing. Okay, that was a stellar vehicle. All right. Now you can get vehicles that get 5, 4. Okay, if they're small enough. All right. You can get big trucks that'll get 7 or 8. All right. And so certainly we've made improvements to all of that. All right. Making some sense? Just to give you a little eye opener on that one. Okay, so systems with moving parts are always going to lose some energy as heat, okay, and that's consistent with the first law and the second law of thermodynamics. First law says energy can't be created or destroyed, but it can always be converted into other forms, and the second law says that energy always flows from high energy to low energy. So heat is always flowing away from a system that has moving parts. Okay, and that represents a loss, okay, of energy. All right, so the energy supplied to your body by food energy has to equal all of the useful work done plus all of the wasted energy, which includes heat and mechanical energy for the parts of your body. Okay, and like we said, heat always flows from hot to cold during that process. So the efficiency of a system can never be 100%. Okay, you're always losing some energy to the surroundings. If that wasn't true, the police wouldn't be able to use the FLIR camera on the helicopter to track down criminals. Right? You guys ever seen that? Okay. Sometimes they'll show the forward-looking infrared. Okay, the infrared heat camera that they have on the helicopter when a guy's running from the police, and no one can find him. You see all these white figures in the picture walking around, looking. They can't see anything, and there's this one white figure that's laying down. Okay. It's dark, they can't see him, he's hiding in a bush, but to the forward-looking infrared, all that heat that you waste, okay, that transfers away from hot to cold, the camera picks up, and you stand out like a sore thumb. All right? Then usually you see the little dog-shaped figure, and then it's kind of funny after that. All right, so efficiency, very simply, it's a percentage, okay? We all know how to calculate percentages, right? You take what you got divided by what you could have got, and multiply by 100. Is that pretty easy? Yeah. That's all you're doing for efficiency. Take the actual work that was done, divide it by the energy you had to put in, and you've got your percentage. Okay? So that's what we're looking at here. Okay? The useful work that was put out, okay? The work that was put in, and you can multiply by 100 if you feel you need to, but most of us can figure out that 0.81 works out to 81%, right? Okay? We don't have to factor in that 100 times 100 thing there. All right, so some machines or systems involve conversions of mechanical energy to another form of mechanical energy. Anytime you convert one form of mechanical to another form, energy is going to be lost. Usually there's going to be some sound, usually there's going to be some thermal energy, okay, things like that. All right, so if we're looking here, automobile internal combustion engine, like we said, anywhere between 12 and 15% efficiency. Okay, an electric engine, 95% efficient, up to 95% efficient. Why is an electric engine so much more efficient than a gas engine? Okay, think back to grade 9 when you built the little electric motor.
Well, basically because almost all of the energy from pushing the forward, whereas the fuel is created so much.
Okay, so partially you don't have any fuel, but we're not going to, I mean, in Alberta, how do we generate electricity? Coal, yeah. Over 90% of the electrical energy used in Alberta is generated by coal-fired plants. So we're still burning energy, but we're just looking at like the motor versus the motor here. So an electric motor, does it have as much internal friction as a gas motor? No, because there's not as many moving parts in contact with each other. If you've ever looked or built or seen the inside of an electric motor, there's tons of magnets in there. All right? And those magnets actually hold each other away, hold the moving parts away from each other. So there's not nearly as many points of contact, so it spins much more freely, okay, than a gas-powered motor would. All right? I mean, you can take any size electric motor, put your finger on it, and spin it, okay, quite easily. Now, imagine starting your lawnmower. It's the same action. You are trying to spin the gas motor. Okay? How do you start your lawnmower? Yeah, you put your foot on it, you grab the starter rope, and you yank with all your might. Okay? Not nearly as efficient as an electric motor that you can spin with one finger. All right? It's a lot more efficient because there's not as much contact between parts. Okay, so they run much, much more efficiently, which is why, obviously, we're trying to put them in more vehicles. Having an electric motor there assisting the gas motor does use less energy. Here's the issue. How do you charge the batteries in a hybrid car? The gas engine. The gas engine charges the batteries. Okay? When you're not using the batteries, the alternator, which charges the battery in any regular vehicle, also charges the batteries in a hybrid vehicle. All right? Now, it's still, when you're running the electric motor, it is still that much more efficient that it is still a benefit to do it that way. All right? It's still that much more efficient. Okay? Does everyone sort of follow me there? Yeah? Okay. All right. Now, in addition to that, on hybrid vehicles, other ways to increase efficiency, and most automakers are doing this. Honda's the one who figured it out first. Okay? They use what's called a thermocouple. We talked about that the very first day. Okay? It's something that directly converts heat into electricity. All right? They put those into the rotors. Okay? And the rotors are the disc-looking part of your brakes. Okay? So they've got these thermocouples in the brake rotors. When you apply the brakes, do they get hot? Yes. That heat is converted into electricity that charges the batteries. Okay, on a hybrid car. It's not a lot, but it's something. Okay? It's enough that the cost benefit is outweighed by the amount of actual electricity that is produced. It's not a lot, but it's something. Okay? So that's another way to do it. Thermocouples aren't really efficient, but they put a little bit more electricity back into your vehicle. So rather than all that kinetic energy you've built up just going away as heat, some of it actually gets converted back into electricity and put right back into the batteries. So things to think about. All right. Now, here's the thing I really want you to consider, because this is one of those things that people that buy an electric car don't think about. Okay. You get sold an electric car because people say you're going to do what by buying an electric car? You're going to save the environment. You're going to reduce your carbon footprint. Okay. That means how much carbon dioxide you put out. In Alberta, are you actually doing that by buying an electric car? No, because in Alberta, we burn coal to make electricity. You're putting the carbon dioxide into the atmosphere one way or another. Okay? If your source of electricity is fossil fuels, you are putting carbon dioxide. You're not reducing your carbon footprint by buying an electric car. Okay? Does it take the same amount of energy to drive to work regardless of what kind of car you drive to work? Essentially. Yeah, it's a trip, right? It takes this much energy to go from A to B. Well, if you use that much in electricity or you use that much in gas, but your electricity comes from burning coal, you didn't really save any carbon dioxide in the long run. Okay? Now, if you live in a place where most of the electricity is produced in a cleaner way, like let's say it's solar or it's let's say hydroelectric or geothermal or tides or wind or something like that, then yes. Okay? Then you might be reducing your carbon footprint, but the reality of it is that in most places, at least in Canada, you're not. Okay? Buying a Volt, okay, is not really saving the environment, at least in Alberta for sure. Okay? But it might be in other places if they're using nuclear power or something like that that doesn't have a carbon footprint. Okay? But that's the thing you have to, if you're making that choice and you want to make a choice that saves the environment, you have to consider whether that choice is really doing what you think it's doing. Okay? And sometimes it's not. Radioactive? Yeah. It's the amount of mass. When you run a coal-fired electrical plant, you're putting like millions of tons of carbon dioxide into the atmosphere all the time. Okay? A nuclear power plant will produce by mass a lot less waste. That waste is obviously quite a bit more toxic. Okay, and also radioactive, which isn't produced by a coal-fired plant. The only way to get rid of that stuff is really you build special places deep in the ground, you encase it in concrete, and forget about it. Yeah. Okay. They're actually considering building a huge repository for nuclear waste in Saskatchewan where they have bedrock that is non-porous. And they would they would dig this deep shaft, essentially with a big holding area at the bottom, where they would put these barrels of nuclear waste. Okay, now that nuclear waste is going to be hot, not temperature-wise, but radioactive for a couple of thousand years. Okay, like you would essentially build this thing, fill it, then pour concrete into it, seal it, and forget about it. Okay. again, the structure of the bedrock is supposed to be able to keep it. Even if the actual containers the waste was in were to rupture, it would be also encased in concrete, also encased in this bedrock that's non-porous, isn't in contact with aquifers and water and stuff like that. So theoretically, no. Reality-wise, who knows? No, at least not right now. A nuclear reactor is big. The smallest thing we have that's mobile and powered by a nuclear power plant is a nuclear submarine. Okay, and those are quite large. No, no. You wouldn't want a nuclear tank. On the battlefield, a ruptured nuclear tank is kind of a problem, right? Well, yeah, but you got to consider that it might be in amongst your lines as well when that happens. So no, it's not practical, right? It's not practical at a small level. Plus, there is that issue of you don't want average Joe Blow to be able to get his hands on nuclear material. There's kind of a lot of regulations and security around that stuff for some reason. Yeah. Some people are irresponsible with the use of said nuclear material. Okay? Yeah. All right. So your steam engines, okay, a steam reciprocal engine, okay, 50 to 75%, steam turbine engines up to 40%. Again, anything that's got moving parts has got friction, okay, but they're still relatively efficient. If you're looking at a nuclear-powered submarine, okay, the nuclear reactor produces what? Produces electricity. Okay, a nuclear reactor is exactly like a steam engine, is exactly like a coal-fired nuclear power plant after the actual heat-producing part. Okay, so we use something that makes heat. That heat boils water and turns the water into steam, and the steam goes through pipes and turns turbines, which are attached to generators, which generate electricity. All right, your coal-fired plant works that way. Okay, a nuclear power plant works that way. Oil-fired plants, they're all essentially the same. Everything comes down to there's a turbine that spins that's attached to a generator. Okay, the wind farm out at Pincher Creek, okay, same idea. Those are big turbines. When they start to move, they're attached to a generator. They generate electricity. Okay, it's just a matter of how did you get the turbine to move. Most things use heating water, steam to turn the turbines, and that's what a nuclear reactor does. Okay, it produces a lot of heat that makes steam and turns turbines. All right, so essentially, a nuclear submarine is an electric vehicle. Okay, all of its engines are electric. All right. No, shielded. Yeah, almost all like big military vehicles are EMP shielded. Okay, which basically means they have a Faraday cage around all of their essential computer components. Okay. Does there? I see a few confused looks. Was it the EMP or the Faraday cage or both? Both? Okay. EMP is electromagnetic pulse. When you detonate a nuclear weapon, it's not just like radiation and heat and all of that. There's also an electromagnetic disruption. Okay. What would happen is essentially anything that's electrical nearby, the charged particles produced by a nuclear explosion can enter a circuit from the air, okay, and they will overcharge it, so they'll just burn it right out. Okay, so if you had a light bulb and you were like holding it in your hand, not that you, and watch the nuclear explosion, it's kind of like that, but okay, the bulb would light up from the actual electrical pulse, okay, the electromagnetic pulse that's produced. The light bulb would light up and then explode. Okay, because it would overcharge. It would be way too much for it to handle, and it happens like that with any electrical circuit. So if you had a laptop fried, okay, your iPhone fried, okay, whatever, anything that has an electrical circuit would be essentially burned up, okay, by the massive electrical pulse that would be produced. So what you do is you surround them in a metal cage, right? So you put whatever you want to protect, your phone, okay, in this cage. Okay, that's all. It looks like a bird cage. That's why it's called a Faraday cage. Okay, and when the electromagnetic pulse encounters these, the electricity is channeled elsewhere, and anything inside is protected. Simple but effective. Okay. They use the same thing. If you ever watched one of those lightning displays, they put a person in a cage, right? And there's this lightning that they produce artificially that's zapping all around. The person stands in the cage and doesn't get hurt. Okay, it's because the cage absorbs everything. Yeah. All right. So looking at an example here. Okay, an efficiency example. If I'm going to have you do an efficiency example on the unit exam, it is not going to be a long answer, or sorry, a written response question. It would be a multiple choice question because it's a pretty easy calculation. All right, so we got a crane lifting a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.30 times 10 to the 4 joules of work while doing 8.0 times 10 to the 3 joules of useful work. All right, so how do I know which one should go on top of this equation? Okay, remembering that efficiency, okay, is the useful work, okay, over the input work. Okay, I mean this question sort of said useful work. That's one way to look for it. But which number's always going to be smaller? The useful work. So if you can't tell from the wording of the question which one is which, the small one always goes on top. If you don't do it that way, you'll have a system that is producing energy because your efficiency will be more than 100%, and that is impossible. Okay? So if you do that on your calculator and you get like 1.5, you did it wrong. Okay? Because you got something running at 150%, which means it's making energy. Okay, by running, and we know that that can't happen. All right, so you got your useful work divided by your input work. So our useful work is this 8,000 joules here, okay, divided by the amount of work that was put in, okay, 23,000 joules. All right, when we do that calculation, okay, we should get 34.8%. Okay, so when you punch that into your calculator, you get 0.348. Okay, everybody all right with that? Okay, is that relatively straightforward? Okay. All right, I would like you guys to try, let's say these three. Okay, we'll go through those together, and if need be, we can do a few more, but I don't think we'll have need for that. Okay, and then we will move on here. Actually, I think I've got a handout with these on it. You guys can start with this, and I'll give you the handout here. All right, so for number one here, we're given the efficiency. Rather than have the times 100 part in there, can we, like in our head, figure out what the decimal is for 15%? Yeah, okay. So we're going to go that 0.15 is our efficiency. Okay. It was used to do 3.2 times 10 to the 4 joules of useful work. Top or bottom of the equation? Top. Okay. So we've got useful work, okay, being 32,000 joules. Okay. So our formula goes like this. The useful work by the input work equals efficiency. I'm trying to find how much work had to be put in. Agreed? This number, IW, is always bigger than UW. Agreed? All right. So if I switch the efficiency, which is decimal 1.5, and this, okay, so divide one side by efficiency, multiply both sides by IW, will I be dividing by a decimal? When you divide by a decimal, does the number get bigger? Yes. All right, so that's what we've got to do here. We're going to have UW over the efficiency, okay, to give us the input work. All right, and so that'll be 32,000 divided by 0.15, and that should give us, okay, sorry, I don't have the answers on there, guys. Are they on your worksheet? No? That's weird. Okay. Come on. All right, 32 on 32,000, okay, divided by decimal 1.5. All right, gives us 213,333 joules. All right. Everybody good with that one? Okay, is that a very hard formula to use? Okay, nay. It's like V equals D over T, right? Okay, it's not too tough. All right, and guys, honestly, like on the exam, the only efficiency question I have is a multiple choice question. All right, so it's not a matter of huge marks, because I don't think that this is really taxing your critical thinking skills very much. Okay? We need to do the other two or no? Go over 3? Yeah. All right, so we got a small electric motor that runs at 85% efficiency. So our efficiency is 0.85. Okay, in lifting a small load, it produces 15 joules of mechanical energy input. We're trying to calculate the useful mechanical energy output of the motor. All right, so we know the input work is 15 joules. All right, so we're trying to find the useful work that's being put out. Okay, input work equals efficiency. Okay, so if I want to get the useful work, I need to multiply both sides by IW. When I multiply by a decimal, the number gets smaller. Okay? And that's what should happen here because UW should be smaller than IW. All right? So 0.85 times our 15 joules there, okay, should give us 12 point something, right? 12.75. 12.75 joules. Okay? That's how much useful work you got out of that thing by putting 15 joules worth of energy into it. All right. Okay, let's move on from efficiency here then. I want you to write that one down and give it a try. That's conservation of energy, EI equals EF. Okay, just like some of the ones we did, not yesterday, but the day before yesterday. I'll give you a couple minutes on that one, then we'll go through it. All right, so we got roller coaster, okay, doing this. Okay, and it is 650 kilograms. Not that you'll need that number. Okay, top of a 55-meter hill, rolling at 4.5 meters per second. Okay, what height will it be at when it is traveling at 20.5 meters per second? How do I know it's lower when it's going 20.5? It's going faster. Okay, it has more kinetic energy than at this point than it has here. And since the mechanical energy has to be the same, it has to have less potential energy here than here. That means it's got to be lower. All right. Here's what we know. There is no mention of work or force in this question. Therefore, the energy is not changing between A and B. All right? Everyone follow me there? Yes? That, and I've told you time and time again that a roller coaster is an example of the law of conservation of energy, and you should always know how to start one of those questions. Okay? So EI equals EF, and that means that the initial potential plus the initial kinetic equals the final potential plus the final kinetic. Everyone okay with that? All right. Then I put in the formulas for these things. Are any of those 0 in this situation? No, they all have some value, some non-zero value. Okay, so mghi plus 1/2 mvi squared equals mghf plus 1/2 mvf squared. I am looking for hf. What should I move first? Right, I should move the final kinetic energy over to here so that I'm essentially doing this. The initial mechanical minus the kinetic energy should give me the potential, because that's how we calculate mechanical, right? We add potential and kinetic. We're doing it twice here. All right, so if I want to find the potential, I subtract the kinetic over to this side. So I will have this mghi plus 1/2 mvi squared minus 1/2 mvf squared equals m times g times hf, sorry. What can I do with the m if I so choose? I can cancel it off. I was given it, but I don't like to do extra work. So I'm going to get rid of it. Okay, now how do I get hf by itself? Divide by g. Alright, so all of that stuff over g, okay, will give me hf. By the way, the answer is 34.6 meters. Alright, so here's what we've got then. We have 9.81 times 55 plus 1/2 times 4.5 squared. So those are the two initial values. Minus 1/2 times 20.5 squared, the final speed, over 9.81. Okay, when we do that, we should get 34.6, but we'll double check. Okay, so we've got 9.81 times 55 plus 0.5 times 4.5 squared minus 0.5 times 20.5 squared, okay, divided by 9.81. 34.6 meters. Okay. Is that making sense? Right. Okay. Would it have worked out the same if I'd have left the 650 in all those places? Yep, would have worked out exactly the same. So if you're not comfortable with canceling the M, or you're not sure if you should, leave it in. Okay? You're fine as long as I give it to you. If I don't, you can come up and ask me. Okay, give that one a try. Ball's thrown upward at a speed of 8.5 meters per second from the top of a 50-meter building. How fast will it be going when it hits the ground? Okay, the first reason throwing, whether I throw this thing up or down doesn't matter, is because if I throw it down, it has initial kinetic energy of 8.5. Agreed? Okay, if I throw it upwards, it's still got an initial kinetic energy of whatever times m, or 1/2 times m times 8.5 squared, right? Okay, doesn't make any difference whether it's up or down because I don't put positive or negative on it when I punch it into the equation, do I? Energy is scalar. It does not care which way that ball is going. All right? Since I'm only looking at this from an energy perspective and not a where does it land perspective, right? It doesn't make any difference. Here's the second reason. If I throw it up at 8.5 meters per second, it will go up, stop, and come back down. How fast will it be going when it gets here? 8.5 meters per second. Okay? It doesn't make any difference which way I throw it. When it gets back to that spot, it'll be like I threw it down at 8.5 meters per second. Okay? Does that sort of make sense? This is one of those cool things that happens with physics. Okay? All right. So we started out same as the others. EI equals EF. Okay? Now, at the beginning, obviously we're above the ground and we're moving. So we have both kinds of energy. What about at the end? Don't have any potential because we're hitting the ground. Height is 0. So we'll just write EKF here. All right, so we plug in our formulas. M times G times HI plus 1/2 MVI squared equals 1/2 MVF squared. Julie? Yes. Okay, trying to find VF. How do I get VF by itself? Divide by half or half of M, depending on whether you canceled the M's or not. Okay, we'll do one here where we don't cancel the M's just to show that it doesn't make any difference which way we do it. Okay, and then square root. Everybody with me so far? Okay. So, I didn't give you the mass, did I? Okay, so we have to cancel M because you weren't given it. All right, so we can't do one where we keep M because we weren't given it. All right, so 9.81 times 50 plus 1/2 times 8.5 squared over 1/2 square rooted, and that should give us 32 meters per second. Okay. Do all of these pretty much follow the same blueprint? Yeah. Okay. The only thing that can change is whether you're solving for a height or solving for a speed. Okay. But up to that point, everything is the same. All right. So once you learn the pattern, these are pretty easy. Okay. Let's try that one. What's the initial speed of this roller coaster? Once again, no mass given. Or make it whatever mass you want. Okay, so if we're looking for the initial speed of the roller coaster here, again, sets up the same as they all do. EI equals EF. Okay, and we've got mg hi plus 1/2 mvi squared equals mg hf plus 1/2 MVF squared. We'll cancel off the m's right away since it wasn't given to us anyway. Okay, and we're looking for VI squared. So what do I have to do with GHI? Minus it over to the other side. Okay, and then what? Divide by half and square root. Okay, so then we plug in our numbers, and okay, and we solve here. I don't know if I have the answer on there. 5 meters per second is what the answer comes out to. Okay, so we'll have was the initial height 40. Oops. Final height was 10. I did so. Nah, now I got too many brackets in there somewhere. Yep, too few brackets. There we go. 5. Finally. Okay, 5 meters per second initially. Okay. All right. Try this one. While you are trying it, I will attempt to find the video of Jackie Chan jumping from one side, from one apartment building to another. Has anyone ever seen this movie? Jackie Chan is insane. He can do the most amazing stunts. The only problem with this movie is it was actually filmed in Chinese, and the whole thing is subtitled and has voiceover. So their mouths are saying one thing, while the actual audio is different.